waves. So we're going to be talking a lot about waves, and you'll see a lot of diagrams. So a lot of diagrams will show waves that look like this, maybe waves that look like this. Maybe it's just particles that are moving. So it can look very different. So let's get started. A wave, in general, is a repeating disturbance or vibration that transfers or moves energy. So we're only moving energy from place to place. So big picture, waves transfer energy. Waves are all about moving energy from place to place. They do not, however, transport matter. So let's say that you're using a jump rope to make a wave. The matter is not moving. The jump rope is not actually moving. It's vibrating up and down, but what's moving is the energy from one side of your jump rope to the other. So how is that? Well, waves are created when a source of energy, so force is your source of energy. You apply a force and it causes that vibration. And again, that vibration is just that repeated. It could be a back and forth or an up and down motion. All right, what can waves travel through? So there's two options. Some waves have to have a medium, or they can use a medium. That medium can be a solid, liquid, or gas. And then sometimes waves can travel through empty space. So empty space is going to be a vacuum with no matter, such as outer space, or in a lab where you can create a chamber where you've sucked out all the air particles and it's just an empty space. So there are actually two types of waves that we're going to look at. The first one is mechanical, and then there's also electromagnetic. So mechanical waves. Think mechanical must have a medium. MMM. Mechanical medium. So mechanical waves must have a medium. And again, a medium is any substance that carries the wave or through which the wave travels. So in essence, a mechanical wave cannot travel through empty space or a vacuum. Examples of mechanical waves include seismic waves. So seismic waves are the waves released when an earthquake is released from Earth's plate boundaries. And the medium for those seismic waves would be Earth's layers. It moves all through Earth's layers. Sound waves, another mechanical wave. Sound waves has to have a medium. That medium is gas particles, but sometimes it could also be a liquid or a sound. Think about it. Sound can go through walls. If you're swimming in a pool and you go underwater, you can still hear people talking and laughing above you. That's because the sound can still move through the liquid. However, it's changing medium, so that's why it sounds a little muffled. You can't really understand people too well. Ocean waves, that's a mechanical wave. The medium would, of course, be the ocean water. A rope or spring waves, you'll see a lot of simulations with rope and springs, and the medium, of course, would be the actual rope or the spring. All right, on the other hand, the complete opposite type of wave is an electromagnetic wave. So these waves can travel through empty space, or they can use a medium. So again, empty space would be a vacuum or outer space. There is an electromagnetic spectrum that has 7 types of electromagnetic waves. So as you can see in the diagram in the bottom, we have radio waves, microwaves, infrared waves or infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. So, of course, light travels in waves. Light travels as an electromagnetic wave, and light is part of this spectrum. Visible light is the light that we see. So light waves are the only electromagnetic waves that we can see with our human eye. We cannot see any other wave with our human eye. We would have to have some sort of assistive technology to see any other type of wave. Now, there are 3 types of mechanical waves depending on how that energy is moving. So, transverse waves, longitudinal waves, and surface waves. So a transverse wave. This is when the waves in which the medium moves at right angles. So that means that if the energy is moving to the right, that means that the medium for the wave is moving up and down. So this creates right angles. See? Nice 90-degree angles, up and down. So other examples, you have a rope tied to an object and you're moving it up and down. The energy is moving to the right. However, the wave is moving up and down. Another example with particles, you have this initial position of particles. All of them, as you can see, are at rest. And then you apply a force, it sends energy through the wave, and now all the particles are being displaced up and down. There are parts to a transverse wave. So the highest parts would be the crest. So every high part would be a crest. The lowest point is a trough. Think about animals that eat or drink out of a trough. Those are on the ground. Troughs are the points that are closest to the ground. They're the lowest point. Okay, compressional or longitudinal waves, you can say it either way, they're the same thing. This is a type of wave where the wave in which the medium moves back and forth. So back and forth or side to side. So it's moving in the same direction as the wave. The energy is moving in the same direction. So let's look at this diagram. Right here is our initial position, and you have just a normal position of a spring. It's just stretched out, it's relaxed, it's not moving. Then you can push or pull on the spring to cause these areas of relaxation or rarefaction, these areas of where it's compressed or compression. So there you have it. The energy is moving left and right because you're pushing and pulling, but also the wave itself is transferring the energy left and right. The wave particles are moving left and right. So it's moving in the same direction. So again, you have it here, waves moving left and right. The vibration of the particle is also left and right, so same direction. Again, the parts of a longitudinal wave. I know we just said it, but here it is on a particle wave. So you have areas of compression here where all the particles are really close together. Then you have areas of relaxation or rarefaction. That's how I remember it. Compression compresses, rarefaction relaxes. And no, it is not rarefaction, it is rarefactions. So these are just areas where the particles are spread apart, they are relaxed. Okay, surface waves, third type. For a surface wave, it is the object travels on a surface separating two medium. So here you can see the little bobber for the fish, for the fishing rod. It is separating two medium, the water and the air. The object on the surface moves in circles, a combination of transverse, remember transverse waves like to move up and down, and longitudinal, which moves side to side. So when you combine up and down and left and right, you do end up with this circular motion as you can see here. So the little bobber starts to move up as the ocean wave carries energy upwards. Then the energy is moving to the right. So the little bobber is moving over to the right just a little bit. And then the energy for the wave is moving downward. And so it continues. So as you can see, the water is just moving in circles, so the bobber is moving in circles. Here is a neat graphic organizer that I found that might help you, so feel free to pause and look through this. So just to highlight a couple of really important parts, waves transfer energy. So they carry or transfer energy. They do not move the matter. The matter stays in place. There are two categories, mechanical and electromagnetic. So we just talked about mechanical. Mechanical can be classified as compressional or longitudinal and transverse. There's also that third type that we just talked about, surface waves, but that one's not heavily focused on for the purpose of this course. So again, mechanical waves transfer energy through a matter called medium. Mechanical waves has to have a medium. The medium could be air, water, ground, objects. The possibilities are endless as long as it's some sort of substance. Examples of mechanical waves. So in real life, sound waves, ocean waves, earthquake waves, all of those are examples of mechanical waves. When we're talking about compressional or longitudinal waves, these waves has the matter compressed and relaxed as the energy moves through it. So you have areas of compression here and areas of rarefaction here. Transverse waves, again, the energy moves perpendicular. So, the matter moves perpendicular to the energy. So it has these nice up and down waves. On the other hand, electromagnetic waves. Notice how it's connected here. Electromagnetic waves are a type of transverse wave. So Electromagnetic waves just have the shape of a transverse wave. They will never be a compressional wave. Electromagnetic waves do not require matter or a medium, but they could use it if it is there to transfer energy. And then there are, of course, the 7 types that we already talked about for the electromagnetic spectrum. All right, if you have any questions, leave a comment.